In the first video, we presented the fundamental postulates underlying the building of special relativity. First postulate, the laws of physics take the same form in all inertial frames of reference, and the second postulate, light has the same speed in all the inertial frames regarding the source motion. Now, we begin to see how Einstein used these two assertions to investigate the very nature of time and space. At first, we have to pay attention to the definition of simultaneity. When can we say that two events are simultaneous? Or to make a step backward, what is an event in the first place? In physics, an event is a phenomenon which happens at a specific moment in a specific place. For instance, if someone is inviting you to a party at the Cascine Park in Florence, Italy, the city where I live, and you want to go there, you will ask, okay, but when does it begin? On the other hand, if you are invited to a party for the next Friday and you want to go, you will ask, okay, but where is it? There is no party, there is no event without a location and a date. In physics, the information about the simultaneity of two events that happens in two different places is very relevant. You want a criterion to establish if two events happening in different places happen at the same time. Einstein asked himself, how can I know if two events are simultaneous? In Newtonian mechanics, time was a quantity flowing in the same way at every place, no matter the circumstances. So you could say two events are simultaneous if they happen at the same time. Einstein observed, how can I say it operatively? That is, can I imagine an experiment, the most simple, which has a positive outcome only in case of simultaneity, and otherwise has a negative one? The answer is definitely yes. Einstein's definition of simultaneity is the following. Two events are simultaneous if an observer placed halfway between them see them occurring at the same time. That is, they are simultaneous if the two events, I see the first event observing it from halfway between the 2 points, and second event, I see the second event observing it from the same point. These events, which happen in the same place for their very definition, happen at the same time too. For instance, two lightnings strike 2 points at the same time if an observer placed halfway between the 2 points receives the light coming from the two lightnings at the same time. By the way, this definition serves quite the same way to the definition of synchronization of two different clocks. Two clocks are synchronized if a person placed in the midpoint between them sees them keeping the same time. A simple but rigorous definition like that, altogether with the two relativity postulates, implies that time, contrary to the Newtonian concept, cannot flow in the same way for all the observers, no matter the circumstances. Simultaneity, with this definition, is itself a relative concept. Simultaneous events for an observer could not be the same for an observer placed in a different inertial frame. For instance, take two observers. The first placed at the center of a train carriage moving straight with constant velocity, and the second placed on the ground nearby. Let two lightnings strike the two ends of the carriage. If the observer on the ground sees the two flashes at the same time, not so is for the observer on the carriage. He will see the flash on the front side of the carriage first and then the other one. Important. Both the observer has the same right to decide if the two lightnings were simultaneous or not. That on the ground sees the two barns on the rails and verify that when he saw the flashes, he were halfway between them. On the other side, the moving observer sees the two barns at the two ends of the carriage, and he knows that he was at the midpoint between them. Nonetheless, the first saw the two flashes at the same time, and the second did not. The front flash preceded the rear flash. There is not simultaneity for him. To clarify this point, suppose to take some pictures of the key moments during the process. From the observer at rest point of view, there is an initial time when the two light pulses were generated. Then, a moment when the mobile observer is seeing the front pulse. Another moment when the observer at rest sees both the flashes, and the last moment when the moving observer sees the rear flash. This is the story. This is the story as seen by the observer at rest. From the moving observer point of view, the two lightnings were not contemporary, and the observer at rest sees them contemporarily only because he is moving toward the back poles. This is intended with the term relativity of simultaneity. Two events that are simultaneous as seen from a given inertial reference frame could not be such in a different inertial reference frame. One could be tempted to object that the real simultaneity is that observed by the observer which is at rest in respect to the ground. But remember the first postulate. Quiet is a relative concept. All inertial frames, whatever their state of motion, are equivalent to express a physical law or to make an experiment. So we are forced to admit the relativity of simultaneity. If simultaneity is a relative concept, clock synchronization has also to be relative. For instance, if the observer at rest has two synchronized clocks near the points where the two lightnings strike the railway, the observer on the carriage cannot see them synchronized. In fact, the observer on the carriage sees the front clock at rest signing 3 a.m. when he sees his clock signing a bit less than that. Then, he sees the rear clock at rest signing the same time when his clock signs a little more than 3 o'clock. Consequently, the observer at rest sees the two clocks on the carriage signing two slightly different times when both his clocks sign 3 a.m. Finally, both the observers sees the clocks of the other observer not synchronized. It will be important to understand how the delay of one of the clocks in respect to the other depends on the distance of the two clocks and on the speed of the train. But this quantitative consideration will be treated in another video. First, we have to study how the duration of a phenomenon also depends on the reference frame from which we observe it. This will be the topic of the next video.